For the last unit of mechanics, we're going to look at circular motion. So far, we've looked mostly at linear motion, where everything happens along the same line. And we had one example of parabolic motion when we were firing cannonballs. For this unit, we need to go back first to Newton's second law and see what it really says. So remember, Newton's second law told you that if there is a force acting on an object, it's going to cause a change in the velocity, known as the acceleration. Now we've treated this equation as if all these things were numbers. But really, force and acceleration and also velocity and position are vectors. And a change in a vector can happen in the same direction as the vector is pointing, but also in a direction that makes an angle with that vector. So if the acceleration is pointing in the same direction as the velocity, what's going to happen is that the velocity, the speed, or the magnitude of the velocity is going to increase. If the acceleration points in the opposite direction as the velocity, the speed, the magnitude of the velocity is going to decrease. But you can also have an acceleration that makes an angle with the velocity. Today we're going to look specifically at the case where the acceleration is perpendicular to the velocity. And then the magnitude of the velocity will stay the same, you'll keep the same speed, but the direction of the velocity is going to change. Now that may sound complicated, it's not actually that complicated, because the acceleration was simply the derivative of the velocity. The derivative of a vector works just like the derivative of a function. It simply tells you how you change over time. So suppose that the velocity is given by this vector at some point in time. And a little time later, it has changed to this vector. Now the acceleration is simply the displacement between the ends of these vectors. So for this change in velocity, where the magnitude has stayed the same but the direction has changed, the acceleration is pointing from one end to the other end. So a force can cause a particle to accelerate or decelerate, what we have seen before, but it can also cause it to change the direction of its velocity. And the simplest example of that is what happens when you start playing with ropes and blocks. Right, so here I have a little block, I have a rope that's connected to it, and I can twirl this around. And you know what happens, this block is going to exert a circular motion. So the velocity of the block is not changing as I do this, but its direction is changing. And that's because of the force exerted on the block by the rope, the tension in the rope. So this circular motion is an example of a motion that's under the action of a centripetal force. Centripetal forces are not a new kind of force, right? They're not like gravity or Hooke's law. They are a net force, the net force that you put into Newton's second law. To illustrate how that works, let me slightly change the example and now start with the block hanging down under the force of gravity, like this. And now if I start spinning it, right, it's going around again in a circle if you look at it from the top. Right? So, or in cartoon form, if the block is already making an angle with the vertical and I'm exerting this tension force on it, it will be spinning around. So I have a gravitational force, I have a tension force in the rope, and I have a net force, which is the vector sum of these two things. And that we call the centripetal force. It's pointing towards the center. And the action of this force, what it will do, if the block is moving at constant speed, but not constant velocity, right, the velocity will be along the circle, whereas the force is pointing towards the center. So then the acceleration is perpendicular to the velocity, and it will only change the direction of the velocity. So how does that work? So we have a velocity that's tangent to the circle, an acceleration pointing inwards, and therefore over time the block will have some displacement along the circle, and in this new position the velocity will still be tangent to the circle and the acceleration will still be pointing inwards. And so every time step we move a little bit along the circle with the velocity and acceleration changing direction but staying perpendicular to each other. Now velocity itself may not even be the best unit, the best quantity to use here, because suppose now I have two blocks on my rope. The block closer to the center will be moving slower than the block farther away. So rather than looking at the amount of meters that you cover per second, you can look at the amount of degrees that you cover per second, or the amount of radians. This is called the radial velocity omega, which is simply just like the velocity is the derivative of the position, the radial velocity is the derivative of the angle that you make. And that is going to be the same for both of these blocks, no matter how far away from the center they are. All right, and then the ordinary velocity is simply the angle times the distance that you have to the center. So it's very easy. If you know the ordinary speed, you can calculate the angular velocity and vice versa. Now, if you are going in a circular motion, you already know how to parameterize that. The motion of a particle along a circle is the radius of the distance from the center with the radius of the circle times either the cosine or the sine. And if we start at the x-axis, then the x-coordinate is going to start with the cosine, and the y-coordinate is going to start with the sine. And now the thing that goes inside, it's the angle, and the angle is changing. If you're rotating at constant velocity, it's the angular velocity times the amount of time. So the description of this motion is given here. And now if you want an expression for the vector that describes the velocity, well, velocity is simply the derivative of the position, so we simply have to differentiate this. Derivative of the cosine is minus the sine, derivative of the sine is the cosine. And if we want the acceleration, we have to take another derivative, and we get the same thing as we had for the position, except that it's multiplied by minus this angular velocity squared. So we can relate the acceleration, the magnitude of the acceleration, to the velocity and the position. And this is how you get this expression. And if you substitute this back into the expression for Newton's second law, you find that the centripetal force gives you a velocity, a constant velocity given by mass times velocity squared divided by the radius. Now this has a minus sign, which indicates that the force is always pointing inwards towards the center. Or if I express this in terms of the angular velocity, I get this expression. Now where do you find this? Well, you can find this in conditions where you're playing with Lego blocks and ropes, but you also find this at very large scales for planetary orbits. The gravitational force that we encountered already in the last unit when we talked about firing rockets is governing the motion of the planets as they go around the sun. And there it's the only force, and it's exerted between the sun and the planet, so it's pointing radially from the planet to the sun. Now the planets are in orbit, so they're making big circles, or actually ellipses, but we'll get to that, making motion around the sun. So in the simplest description, if we describe this orbit as a circle, we have a centripetal force given by the force of gravity. So Newton's law of gravitation for this case, again, is the mass of the two objects times each other divided by the distance squared. So now one of the masses is going to be the mass of the sun, the other mass is going to be the mass of the planet. And this is then equal to the centripetal force for which we just found an expression. So if we equate these two things, we get this relation, and you see that again the mass of the planet is going to drop out, just like we had for the mass of the rocket in the last unit. And we find a relation between the angular velocity and the radius of the orbit for a stable planetary orbit. This relation was already discovered even before Newton formulated his laws of motion. This is known as Kepler's third law, which tells you that there is a relation between the distance of a planet to the sun and how long it takes this planet to complete one orbit around the sun. And the nice thing here is that those are two quantities that you can measure. And what you see is that those two quantities are related by the product of the gravitational constant, which is a universal constant, and the mass of the sun. So we can use this to actually weigh the sun. We can simply plug in the distance between, say, the Earth and the sun for r, and the period that it takes Earth to go around the sun, which is 1 year, and find out what the mass of the sun is. But this doesn't just hold for Earth, it also holds for Mars and Jupiter and all the other planets, and indeed, if you plug this in, you always find the same value for the mass of the sun. We can use the same trick to find the mass of the Earth, because now the central object is the Earth, and the object that's going around it is the Moon. So we find the distance from the Earth to the Moon, and we find the orbital period of the Moon, and we get the mass of the Earth. We can't use it to find the mass of the Moon unless we send something in orbit around the Moon, which by now we are able to do because we can set satellites that orbit the moon and other planetary objects. So Kepler, who actually preceded Newton, could not explain this. This is simply what he observed. And Newton's theory, Newton's mechanics, allow us to explain this from the concept of forces, combining Newton's second law with Newton's law of gravitation. Now, this is Kepler's third law, so there's probably also a first and a second, which is true. The first law tells us that planetary orbits are not actually circles, they are ellipses. That makes the thing a little bit more complicated, because for an ellipse, the velocity is pointing along the ellipse, but the velocity is not exactly perpendicular to the acceleration. So you get a more complicated problem that you need to solve. Fortunately, for that, there is another conserved quantity next to energy that you can use. And this is something that you will encounter if you study physics in your first year at TU Delft. So this concludes the mechanics unit. We've seen how you can use forces and energies to solve mechanics problems. And in the next two modules on electricity and magnetism and on waves, you will use some of these concepts to describe other kinds of phenomena.